Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about shell conduction in CFD. So just to start with a quick overview of what I'm going to talk about today, I'm going to talk about what effect does shell conduction have on the wall heat fluxes. I'm then going to talk about how is shell conduction different to adding a wall thickness, and finally I'm going to look at how does the CFD code solve for shell conduction. So before we dive in and look at shell conduction, it's important for us to consider the wall treatment in the energy equation when there's no shell conduction present. So when we have fluid elements connected directly to the wall. Now, the wall heat flux for this case is given in equation 1. So the wall heat flux Q is given by the product of the density ρ, the specific heat capacity Cp, and the thermal diffusivity alpha multiplied by the temperature gradient in that cell. So just as a quick reminder to you, in some of the previous videos, what I've been through is the temperature field and all other fields vary linearly across the cell in the finite volume method. And so what that means is the temperature gradient between the cell centroid, Tp, and the wall, Tw, is given by Tw minus Tp over Yp, where Yp is the distance to the wall. And just to reiterate that, that's because the temperature gradient across the wall in the finite volume method, across the cell, is always linear. Now, some of you may remember that in a turbulent flow, sometimes our cells are too large for the true variation of temperature across the cell to be linear. And what we do to accommodate that is we modify the near wall thermal diffusivity alpha. And if you need a recap of that and would like a bit more detail, I advise you go back and look at my previous video on temperature wall functions, which I'll link in the description below. And for equation 1, where does equation 1 come from? Well, equation 1 is a slight rearrangement of Fourier's law for heat conduction, which is given there on the right hand side in the square brackets, just as a reminder for you of where that equation comes from. Now, also just as a further reminder for you, for a fluid connected directly to a solid wall with no shell conduction, the near wall thermal diffusivity alpha is given by K over rho Cp when Y plus is less than 5. So remember that this is the treatment we use if our cell is in the viscous sublayer of the boundary layer. If our cell is sufficiently small, then the true variation of temperature across the cell is linear, and we use K over rho Cp to get the thermal diffusivity. But when our cell is large, that means our cell is in the log law region of the universal law of the wall, we modify the thermal diffusivity to account for the temperature profile in the true variation being non-linear. And we modify that so that the product of alpha and the temperature gradient gives us the correct heat flux. So this is the standard treatment for a cell when our fluid cell is connected directly to a wall with no shell conduction. So what happens when we introduce shell conduction into the model? The first thing that happens is the CFD code grows the shell elements away from the wall into the fluid. So you can see in the diagram on the slide there, the left image shows the original cell, and then the second image shows what happens when 3 shell layers are grown away from the surface. So the boundary, or the wall, stays in the same place, but the shell elements are grown away from the wall towards the centroid of the cell. And naturally this means that the wall distance, Yp, reduces, but also the temperature of the inner surface of the wall, Tw, is now unknown. And the reason for that is when we specify boundary conditions, we're specifying the boundary temperature Tb on that bottom wall there, which remains constant. And in order for us to determine the heat flux away from the wall, we know TB, that's the boundary temperature we apply, and TP is going to be the temperature at the cell centroid. However, the wall heat flux is given by the gradient in the fluid there, and so the temperature TW is now unknown, and we don't know what that wall temperature is. And that's what a lot of the mathematics and the explanations that I'm going to give you revolve around. How do we work out what TW is? Because once we know what TW is, then we can use equation 2 there to calculate the wall heat flux and use the same treatment as we would do for a normal fluid cell without any shell conduction. So before I go in to discuss how the CFD codes do that, the first thing I'm going to do is describe the difference to you between adding a wall thickness and adding shell conduction. And the reason for this is CFD codes like ANSYS Fluent give you the option of applying a wall thickness or applying shell conduction. And it's important to know what the differences are between these two treatments. And the way I've done that for you is provided 2 diagrams on this slide to explain the difference. The image on the left shows the effect of adding a wall thickness, and the image on the right shows the effect of adding shell conduction. And as you can see, in both cases, the shell layers are grown away from the surface into the fluid. However, when we add a wall thickness, the heat flux is normal to the surface only. So you can see the red arrows there showing the direction of the heat flux QW. However, with shell conduction, there may also be a heat flux along the surface of the shells. So if we're thinking about our boundary and our fluid, shell conduction allows heat to also be transported along the surface of the wall. And that's the key conceptual idea that you need to think of when choosing shell conduction over a wall thickness. And now we're going to have a little look at the mathematics and the theory, starting with wall thickness because it's simpler. So when we add a wall thickness, the way to think about it is given in the diagrams that you can see there on the slide. The diagram on the left shows the treatment when there is no wall thickness, and the diagram on the right shows the effect of adding 3 thickness layers to our cell. And as you can see in the diagram on the left, we have a wall distance YP, and we have a temperature at the cell centroid TP, and a temperature at the wall TW. And all of these are known, so we can calculate the wall heat flux. Now, with the diagram on the right, we see that because the variation in temperature is linear, we see that TW is reduced, and it's between TP and TB. So if you think of TB as a hot surface and the fluid is cool, then the inner surface there, TW, will be cooler than the boundary condition. And what we also find with the 3 thickness layers is that the wall distance YP is also reduced. And because both of these quantities are reduced linearly, we can see that the gradient there in the fluid cell remains the same. So TW minus TP over YP remains the same if we have 3 thickness layers or if we have no thickness layers. The gradient of temperature between that wall surface there, TW, and the centroid of the cell, TP, is the same. And what that means is that the heat flux that's emitted from that boundary surface, TB, at the bottom, which then enters the fluid cell at the top, is the same if we add a wall thickness. So adding a wall thickness has no effect on the wall heat flux, QW. And the reason for that is the heat flux can only travel in one direction. The heat flux can't leak out of the cells on the side. And so any heat flux that's emitted from that boundary surface TB will always enter the fluid cell above it, regardless of the number of thickness layers that we use. However, what we can see from the diagram on the right there is that adding thickness layers has the effect of reducing the surface temperature. So when we post-process the results and look at them, the temperature of the wall there, TW, will be lower than the boundary temperature, TB, that we apply as a boundary condition. So those are the 2 key things to remember for a wall thickness. there are no change to the wall heat flux. However, the wall temperature there, which is in contact with the fluid, is reduced if we have a hot boundary surface there, TB. So what effect does shell conduction have? Now, the way we're going to look at shell conduction is with a very simple example so that you can understand exactly what's happening. And the example I'm going to use is given there on the slide, where we've got two cells, cell 1 on the left and cell 2 on the right, and both of these cells have a boundary temperature TB, which is constant and the same. And these two cells are connected to fluid elements above them by 3 shell conduction layers. Now, as is the case in most fluid flow problems, the temperature of the wall there, TW1 and TW2, is going to be different. The reason they're going to be different is because of the flow conditions in the fluid above the boundary. So TW1 and TW2 are generally going to be different. And for this example, the ends of these shell conduction elements are insulated. And this is the case in a real fluid scenario problem where we have one boundary with shell conduction applied, which is connected to another boundary that doesn't have shell conduction applied to it. And at the boundary between these boundary conditions, the ends are insulated, so heat will not leak out of the sides here where we can see the red on the slide. However, because we do have shell conduction, heat is free to transfer between the cells within those shell conduction layers. And now we're going to look at what effect does shell conduction have on the wall temperatures TW1 and TW2. So initially, TW2 is at a higher temperature than TW1 there, and the temperature variation between those cells is of course linear and is given by the blue lines which you can see there in the diagram. Now, as shell conduction is turned on, what will happen in the shell layers is that heat is going to be transferred from the cells on the right to the cells on the left, or from the hot cells to the cold cells. So in addition to the heat flux coming off the inner boundary there, we've also got heat conduction travelling through the shell layers from the right to the left. And with this heat transfer, what we find is that the temperature of the wall TW2 is going to reduce, and then the temperature of the wall TW1 is going to increase. And what we can clearly see here from the diagram is that shell conduction has the effect of balancing the surface temperatures, and the degree to which the surface temperature balances depends on how conductive the shell elements are. So this is why when you turn on shell conduction, you have to specify the material and its thickness, because a conductive material, so a material with a high thermal conductivity and a small thickness, is going to be better at balancing the temperatures than a material that is a poor conductor of heat. And you can see the effect in the diagram on the left and the diagram on the right there on the slide. The material on the left is a good conductor, so they may be very thin shell elements, or it may be a material that's very conductive, and the diagram on the right shows a very poor conductor. And we can see that as we get a better conductive material, the surface temperatures tend to balance more. And of course, in the limit of a perfectly conducting material, the surface temperatures would balance out completely. So the next thing to think about is what effect does shell conduction have on the wall heat flux? So on that right cell there, we saw that the temperature was reduced because the heat is now flowing from the right cell to the left cell, and the temperature of the left cell is now increasing because we've got that additional heat flux there into the cell. And what that means, if we now think of the heat given off the surface, we see that the heat given off the right cell is reduced and the heat given off the left cell is increased. However, because the ends of these shell conduction elements are insulated, the total heat flux removed from the surface is the same. So the way to think about this is with equation 4. Q1 and Q2, the total is the same, however the distribution of the heat flux from the surface has been modified by putting on shell conduction. And so what shell conduction is doing is shell conduction is not only changing the surface temperature distribution, smoothing it out along the boundary, but it's also redistributing the heat flux so that the heat flux given off the surface is more even as a result. So the next thing to think about is, when is shell conduction needed? And now that we've got a good understanding of these effects, we'd like to think, when would it actually be appropriate to apply shell conduction to a model? And the way to think about this is, shell conduction should usually be turned on when the heat transfer through the thickness of our surface is important. So an easy example might be a hot pipe, which you can see there in the diagram, where the internal surface of the pipe is very hot, maybe it's at a hot temperature, and then the outer surface of the pipe is cooled by a fluid, and the pipe is perhaps very thick or has some insulation on it. And what will tend to happen is that due to variations in the outer surface temperature, we're going to get heat conduction going along the pipe there. And in some cases, we may be able to mesh actually the thickness of the solids there and solve the entire problem as a conjugate heat transfer problem. So in this example, we would mesh the inside fluid, we would mesh the solid element, and we'd mesh the external fluid and solve the entire thing as conjugate heat transfer. But you may imagine for some industrial processes, the surface topology and the surface geometry may be very difficult to mesh, and it may even become too expensive to solve the full conjugate heat transfer problem. And in these scenarios, the shell conduction model is a good simplification that can get us a good low resolution estimate of the heat transfer along the surface of the object. So now that we know how shell conduction works, and we've perhaps got a good initial idea for when it might be needed, how does the CFD code solve for shell conduction? The first thing to think about is, what are the governing equations for heat conduction in a solid element? And the equation for heat transfer in solid or shell elements is given there in equation 5. On the left hand side, you've got the unsteady variation of temperature, and then on the right hand side we've got the diffusion term, or you can think of it as the conduction term, and then the final term on the right hand side is a source term, a source of heat in our shell elements. Now, this is a standard partial differential equation that you may have seen before. It takes a very similar form to many others. Of course, there's no convection term because there's no fluid moving in the shell elements. And now if we think of the boundary conditions for this partial differential equation by looking at the diagram there, we see that the inner surface is at a temperature TB, that's a Dirichlet boundary condition, and then the surface in contact with the fluid is also at a fixed temperature TW, and that's also a Dirichlet condition. And then the end surfaces of the shell elements are insulating boundary conditions, or Neumann boundary conditions. So for the 4 shell elements we've got there, we can see that the boundaries of all of the surfaces are well defined, and we've got a partial differential equation there, and our CFD code will allow us to set up some initial condition for the problem, and we can solve the equation for the temperature distribution in the shell elements. However, there's one problem with this, and that is the temperature of the wall that's in contact with the fluid is unknown. This is something we mentioned right at the start, that by growing those shell elements off the surface, the temperature of the surface in contact with the fluid, TW, is unknown. And if we were to use a wall thickness approach, of course the variation is linear, and so we could calculate this. However, because for shell conduction we've got heat transfer along the elements, we don't know what the surface temperature is, TW. And this is particularly important because we need this temperature, TW, for both the shell conduction equation and also the fluid energy equations. So how are we going to determine this temperature, TW? Turns out there are 2 different approaches you could use, and some CFD codes will use a different approach depending on how they're set up. The first approach is to use a sequential approach to calculating the wall temperature. And the way you might do that is by first taking an initial guess for the wall temperature TW, and then solving the energy equation for all of the fluid cells in your mesh, and then using the same temperature TW, solving the shell conduction equations for the temperatures in the shell elements. And then of course, after solving these equations, what we then need to do is update the wall temperature TW. And the reason for that is there will be some heat conduction along the shell elements. And the way we do the updating is we use central differencing, which you may have heard me talk about in previous videos, but as a small reminder, central differencing is just going to be linear interpolation between the centroid of that fluid cell and the centroid of the shell conduction centroid there, which I'm going to call TS for the moment. And you can see in the diagram it's just going to be linear interpolation, and the equation you want to use for that is given in equation 6. Noting of course that we are in three-dimensional space, and so the linear interpolation has to use the vector coordinates and the vector distances between the two centroids. So that's the first method we could use, a sequential approach, solving for the fluid, then the shell conduction equations, and then updating the wall temperature there using central differencing. What is another approach we could use? Well, an alternative approach we could use, first what we need to do is think about the energy equation that's solved in the fluid cells. And just a reminder for you, the energy equation that's solved in the fluid cells in its general form is given there in equation 7, where the unknown there is capital E, which is the total energy, which is the sum of the internal energy and the kinetic energy in the fluid cells there. And the reason I'm using the general energy equation here is, remember from my video on the energy equation that the flow may be compressible in some instances, and if the flow is compressible, there's going to be an interchange between mechanical and internal energy there, and so we have to solve for the total energy of the flow, rho E. And of course you can see there, if you examine the total energy variable E, you can see that the temperature is coming in through the enthalpy H there. So really it's a very similar form to the enthalpy equation you've seen, but just extended to account for compressible flows. And if you'd like more detail on that, I'd advise you go back and just have a quick look at my lecture slides on the energy equation, and that will quickly be explained to you. But in terms of shell conduction, what we need to think of is, if we look at equation 7, which is the energy equation for fluid cells, and if we substitute in a velocity of 0, so setting u equal to 0, and a pressure P of 0, as we might expect to find in the shell elements, then we find that equation 7 quickly reduces to the shell conduction equation that we saw previously. Of course, noting that most of the terms there will disappear, the convection term will disappear, and those final two source terms on the right hand side will all disappear when u is equal to 0. So by using this simplification, what it means is that we can actually just solve a single energy equation for the total energy E for every cell centroid in the mesh. So solving the fluid and shell elements together as one complete equation. Noting of course that if we have a shell element, then we set the velocity and the pressure to 0 in those cells. And by using this combined approach rather than a sequential approach, we don't need to do any additional interpolation at the end of a time step. We can just solve the complete energy equation, and that will get us the temperature in the fluid cells and in the shell elements. And of course, with this approach, we're really implicitly ignoring that fluid shell boundary there when we're solving the energy equation. And of course, a small side note here that with this approach, we can still account for that logarithmic temperature profile in the wall adjacent fluid cell there. And the way we do that, same as before, is by modifying the near wall thermal diffusivity alpha W. So the combined approach and the sequential approach can both account for shell conduction and the logarithmic profile in the wall adjacent cell. So just to wrap things up in what's been quite a complicated talk with some key points for you to take away and remember. The first point to note is that when turning on wall thicknesses or shell conduction, the CFD solver grows shell elements away from the surface of the wall into the fluid to create these shell elements. Then, if we choose to turn on wall thickness will change the surface temperature of the wall that's in contact with the fluid, but will not change the heat flux at all, because the heat flux cannot transfer outside the sides of those wall thickness elements and can only travel normal to the surface. Now, if we choose to turn on shell conduction instead of a wall thickness, then what happens is the wall surface temperature distribution and the wall heat flux distribution will change along the surface, and shell conduction will have the effect of smoothing out the surface temperature and the wall heat flux, which tends to give a more physical representation of the real surface temperature in our fluid systems. So just to wrap things up, I'd like to thank all of you once again for continuing to support my channel. I really do appreciate it, and I love hearing all of your comments, feedback and discussions in the comments section. And just a reminder that if you're enjoying the content and you found it really useful, let me know in the comments section. And if you'd like to support the channel, you can leave a donation through PayPal or even buy me a coffee if you want. And links to do that, of course, are in the description below. And once again, I'd also like to give particular thanks to my patrons for supporting this channel. I really do appreciate your support, guys. And if you too would like to support the channel through Patreon, there's a link to that in the description below, and you get a number of additional benefits for supporting me through Patreon. All of the lecture slides that I produce on YouTube, I upload straight away to Patreon, and so you can get those for free if you want to study them in your own time, perhaps print them off and use them as useful references. And also on Patreon, you get free access to my Fundamentals CFD course, which goes from first principles and actually looks at developing your own CFD code in a lot more detail than I can cover in these YouTube lecture slides. And if you want, you can always go and pick that up from my website as well, and a link will be in the description below for that as well. And just to wrap things up by saying thank you all very much for watching. I hope you find it useful, and I look forward to hearing from you in future.